Alright, hi you guys. And today we'll be talking about exponential functions with bases other than e. Okay, so first off we're going to talk about the differentiation of natural log of x, which is 1 over the absolute value of x, and the derivative of natural log of absolute value of x is 1 over x. Okay, so those are some cool unique properties right there. Okay, now the derivative of a to the x, and a could be any number, it just has an x in the exponent, would be a to the x times the natural log of x. Okay. Now the derivative of log base a of x, okay, so let me move that a over a little bit so you can see it, is going to be 1 over the x times the natural log of a. Okay, and some stuff to also remember too, especially in this one right here, that a to the x is equal to e to the x times the natural log of a, and that's where this actually all comes from. And this part right here actually helps explain why the power rule works the way it does, is x to the n is n times x to the n minus 1 if you look at your rules of logarithms, and that's why logarithms are so important, especially in calculus. Okay, so let's actually try out some problems. Okay, so right here I would just do chain rule right here. So the derivative of this natural log is going to be 1 over the actual function. Now since this is x squared, we're pretty much not going to go into negative territory. Okay, so we can draw this out, and on top we would have our 1. Pretty simple. And then on the bottom we would have our x squared minus 4. Okay, and then we would do the derivative, and we would times this by the derivative of the inside function, which would be 2x. Okay, and so essentially this just turns into moving the 2 up here. So let's get rid of that. Let's get rid of the times. There we go. So this essentially becomes 2x over x squared minus 4. So that's some really nice differentiation skills right there. Or at least some help to actually work with it. Okay, now natural logarithms actually do save our tails more than once when we're working on problems like this. So if we had to find the implicit differentiation of y equals x squared times, or x squared plus 3 times x squared plus 1 to the 1/2 power all over x minus 2, and x had to be greater than 1, okay, we would actually have a lot of hard troubles with this. So the best way to start breaking this down is to actually take the natural log of both sides. So we did the natural log of both sides. Okay. Now what's going to happen is that when I do the natural log of this, so let's say I just did the natural log up here, well, if I do the natural log of the whole thing, well, guess what? If I use my rules of logs, that's division, so this becomes the natural log of, let's say, x squared plus 3 times x plus 1 raised to the 1/2 power, let's put that in brackets, minus the natural log of x minus 1. Or, no, sorry, not x minus 1, x minus 2. Okay? And so we could actually break it apart into that. Okay, now if we start rewriting stuff, so this is natural log of y equals, now if you notice this is actually times, so guess what? That's the addition. So the natural log of x squared plus 3 plus the natural log of x plus 1 raised to the 1/2 power minus the natural log of x minus 2. Okay, now if you notice, those are 3 separate differentiation parts, and since we're differentiating with respect to x, okay, look at that. That is beautiful. We can actually start setting this up and working on this a little bit easier. Now the one thing I do recommend is that you notice that this is to the 1/2 power, so you bring it in front as a 1/2. So it should look like, okay, so that it's going to be something like this. Now this is a lot easier to actually work with. Okay, so we're going to have to do chain rule 3 times here. So this one is going to be 1 over y dy dx Okay, so that one's pretty simple. And then this one is going to be 2x on top. Okay, and then on the bottom is going to be x squared plus 3. Let's put parentheses in front of that. Okay, because if you remember, that's the derivative of the natural log of x squared plus 3. Alright, and then it's going to be plus, okay, and it's just going to be a 1 on top because the derivative is just going to be 1. And then on the bottom we're going to have 2 times, well, we can go ahead and distribute it, so that would be 2x plus 2. Okay, and that would be in parentheses. I just like to keep things in parentheses, just so it makes the job a lot easier. But then minus, okay, and if you notice, this is the derivative of x minus 2 is just going to be 1, so that's just going to be a 1 up top. But underneath, we're going to have x minus 2. Okay, so I have everything all set up, except now I still have this 1 times y. So what I'm going to do is I'm going to multiply both sides by y. So when I get everything all set up, it's going to look definitely like this. I'm going to get rid of this part right here, and voila, I'm left with the implicit differentiation of this. Okay. Alright, now when x is greater than 1, okay, if you notice way back in the beginning we had y defined already. So what I'm going to actually do is rewrite this whole thing. So dy slash dx is going to be equal to parentheses, and this is going to be awfully funky looking, so I'm going to go with some big parentheses. And voila, here's what it's going to end up looking like. Your implicit differentiation with respect to x. Okay, alright, that's it for working with exponential functions with bases other than e. I'll talk to you guys later. Bye.